So last lecture was about a pigeonhole principle. So we have seen that if there is n balls and k baskets, right? And if the n balls are put into k baskets, and if the k is less than n, then there is at least one basket contains two or more balls. So I have done this illustration with pigeons and holes. So you can have your creativity. Okay, so there is many applications are there in many branches of mathematics. Today I am going to look at the application of a pigeonhole principle in graph theory. Okay, so graph theory is about it is a combinatorial objects like some vertices and edges. I'll give you some basic idea about graphs. So graph is basically contains vertices and edges, right? And there is a relation between them. Okay, so normally we are going to do about simple graphs. So I'll tell you what is that means, but for time being, vertex, let us choose like 1 to n, 1 2 3 up to n, so denote like box n, right, in this context. Okay, so now edges are subsets of this notation I am choosing. This means box n choose 2, like that's a notation. That means all 2 element subsets of n, right? So normally if you like I denote x2 if x is a set, so then I denote like 2 element subsets of x. Okay, so this is 2 element subsets of the vertex set. Okay, so edges are subsets of that. So I'll give you examples. For example, let us talk about a graph like having set is 1 2 3 and the edge sets are 1 2 and 2 3 because they are 2 element subsets. So this is the idea. So you have vertex 1 2 3 and the connection is given by like this: 1 2, this is an edge, and 2 3, this is an edge. So this explicitly gives you the structure of a graph. Okay, and this is possible because they are simple. So what is simple means, suppose I consider an edge like this. You have one vertex and a loop, we call a loop, right? So that's what we that is a loop. So in a simple graph we avoid this. Also a multi-edge between every any pair of xy there is at most one edge, we assume. That is a simple graph. If there is more than one edges, we call it as a multi-edge, and we don't allow that in our simple graph. Okay, so that's we avoid that. So simple graph avoids these both. There is no multi-edge, right? Yeah, there is no loop. So simple graphs are graphs with vertex set having at most one edge between the pairs of vertices, right? And the loop is not available. Okay, now let us define a quantity called degree of vertex. That is nothing but number of edges adjacent to V. For example, here this is your V and your ABCD as the vertices which is adjacent by an edge. Alright, so the neighborhood of V is ABCD, that we can call a first neighborhood, right? That means it is a directly connected to using an edge. If there is another vertex here, let's say K, then maybe I can say that it is second neighborhood of K. K is in the second neighborhood of V. Okay, so just neighborhood means it's the first neighborhood. Okay, so the ABCD is there, and the degree is the cardinality of that. That's 4 number of elements in the neighborhood of V, first neighborhood of V. So that is degree of V. Now let's talk about a special class of graphs, which is complete graph on n vertices. Suppose we have a vertices n, and we already seen that every pair of vertices can have at most one edge. But in the case of complete graph, we assume that exactly one edge between them, right? Every pair of vertices having one forms an edge, right? So for example, if you take about K3, that means if you label 1 2 3, between every vertex there is an edge. like here also between every vertex there is an edge, right? So here also 1 2 3 4 5 between every vertex, so that's k5. So it goes on like kn means you have n vertex like that, and every edges are present. So the number of edges are basically NC2, because the number of ways to choose 2 element subset is there's NC2 edges. So right, okay. So a simple graph, so from this we can see that a simple graph on n vertex can have at most NC2 edges, because we counted every possible edges. Okay, so a simple graph can have at most NC2 edges if it has n vertex. Also note that if in a graph G, right, if you take a vertex, the degree is also at most n-1, because in a complete graph, if you look at a particular vertex is connected to all n-1 of the vertices, so the degree is n-1. So neighborhood can have at most n-1 element, exactly n-1 if it is a complete graph. Okay, so these are the things. So degree of phi can at most n-1. It is equal to n-1 when the graph is a complete graph. Okay, now we go for the proposition. First proposition: in any graph there exist two vertices of same degree. So I'm talking about multigraph now. You can verify it in the what we call allowing everything loop and this. So we are talking about a simple graph. Right. So they are telling that there exist two vertices of same degree. So this may not be true for multi-adjacent loop. If you let me just try here. If u and v, so here there is a loop. Okay. So the degree of u is 2, but degree of v is it's of course greater than 2, because already there is a loop. We count it as like a 4. A loop will form 4. So it is actually 4. So in this case, what happens is there are only two vertices, right? And the theorem says there exist two vertices have same degree, but they don't have same degree. So it will not work if in multi-edges side. So the graph is a simple graph. In any simple graph, there exist two vertices of same degree. If you have allow loop, it will not work. Right. So let's talk about the proof. So let G be a graph with n vertices, right? Okay. And we know that the degree of the vertex is at most n-1, right? We just see it happens in complete graph. Now what we are going to do is we want to consider an equivalence relation. It's a very easy relation, and we define this on the vertex set. It's very easy. We say that a vertexes are related if they have same degree. If u related to v, right, through tilde, there is a relation, right? If the degree of u is equal to degree of v. So that's very simple. If two vertices have same degree, they are related. So this is an equivalence relation. We can easily verify that. You verify. That's not very difficult to see. Now, what is the maximum possibility? Whatever the graph, the maximum possibility degree can be 0, degree can be 1, and degree can be n-1. Depends on the graph, it will change. So maximally it achieves at -1 if the complete graph comes in picture. Now what is the idea is, you know that the equivalence clauses basically partitions the vertex set, right? And the equivalence clauses are the subsets of the vertex set. So equivalence class can minimally they contain at least one element, right? So what is the maximum possible number of equivalence classes? N. Because every equivalence class contain one fellow, then it is the maximum number of equivalence classes you can achieve, that is n, right? So it is at most n. Now we will keep the case of equal to n. Okay, before that let us consider, suppose k is the number of equivalence classes strictly less than n. If it's strictly less than n, that means then we are partitioning the vertex set. The vertex set contains n elements, so every n element has to be in some equivalence class, right? So suppose the equivalence classes are less than number of equivalence class k less than n, then then by pigeonhole principle what happens? So now the pigeons are the vertices and the holes are equivalence classes. So these pigeons are put into that, then definitely there will be at least one equivalence class, because k less than n, there is at least one equivalence class contains two or more elements. Suppose we have such a equivalence class. What is the meaning of that? Suppose the equivalence class contain u and v, then what is the property? They have same degree. So that's what we have to prove. Okay, so this is a case when it's strictly less than n. Now I assume that, suppose what happens if the equivalence classes are exactly equal to n, then what is actually happens, right? If the equivalence classes are exactly equal to n, k is equal to n, then each equivalence class contains exactly one vertex. There is no other way, right? Now in particular, if you look at the equivalence class of 0, right? The 0 is an equivalent, it's a degree, possible degree. So that contains one element, so let it be 0. So degree of u equals 0. There is a u such that degree of u equals 0, and also there is a v such that the degree is n minus 1, because every equivalence class contains exactly one element. But the problem is u has no neighbors. Degree of u equals 0 means u has no neighbors, but v has, everyone has a neighbor, right? So that's a contradiction. If v has everyone as neighbor, then you must have v has to be a neighbor of u also, so degree of u has to be at least 1, but that's a contradiction. So that means u has no neighbor, v has everyone as neighbor, that is a contradiction. That is not possible. So k equal to n case is not possible, so always k less than n, and when k less than n we can use PHP. So in any graph there is at least two people have same degree, right? That's the idea. Now we will study one more notion about graphs, which is called connectedness. So connectedness means whenever you have a graph, and if you take any two vertices, we can travel through vertices from x to y. So there is a path from x to y. That's the idea. So if this happens if you take any two vertices, there is a path, we call that the graph is completely connected, right? Yeah. So one more way, again we can define any equivalence. Connectedness can be defined in other way, right? So if two paths are connected, two vertices are connected, if there is a path between them, then that is also an equivalence relation. So the equivalence classes are called connected components, and the equivalent if there is only one equivalence class, we call the graph is connected. Another way of formulation, you can think, right? Not very difficult, but basically if two vertices, for any two vertices there is a path between them, we call that connected. Okay, we need that for the next proposition. So the proposition is telling that let G be an n vertex graph, right? Now if every vertex has a degree of at least, okay, if every vertex has a degree of at least n minus 1 by 2, right, then G is connected. So for example, if you have a graph of 7 vertex, I mean, okay, whatever it. So, or you can take any, okay, 7. So now, if every vertex is, this is 7 vertex graph, so every vertex have 6 minus 1 by 2. What is that? Or 7 minus 1 by 2, that is 6 by 2, 3. So every vertex has at least degree 3, then that 7 vertex graph is connected graph. That's what this theorem says, right? Okay, let's prove that. So the proof is going like, let us choose two fellows. What do you have to prove? Having this condition, we have to prove that there is a path between x and y, right? That's what our idea. Now let's choose two fellows, x and y, right? Now arbitrarily we can choose that. Then we have to show that there is a path, right? Yeah. If they are adjacent, we are done, right? Then there is a path, we are done. Suppose they are not adjacent, so that's where we want to make use of PHP. So suppose they are not adjacent, then let's use this picture. X and not adjacent means they are not connected by an edge, right? Okay. So what is our aim is to exhibit one more vertex here that connects, or one or two, anyway we have to find a path. So this is non-adjacent, x and y non-adjacent, and you know that for x and y, for every vertex at least n minus 1 by 2 edges are there, right? So n minus 1 by 2 edges are there. For x has n minus 1 by 2 edges, and y has an n minus 1 by 2 edges, at least. So totally how many edges are present now? Now you have n minus 1 by 2 plus n minus 1 by 2 means n minus 1 at least. So there are at least n minus 1 edges are present total, just in this context, right? Just looking at x and y, right? But how many vertices are there? Here you have to see differently, edges and vertices. So vertices are n minus 2 because already we took two fellows as the red vertices, right? Right, so already we have taken out. Okay, so there are n minus 2 vertices. Now at least n minus 1 edges are there, at least. So that means, since right, so that's the idea. Now these edges must be incident to some vertices, right? So that means these n minus 1 edges are incident to these n minus 2 vertices. So here the pigeons are edges and holes are the vertices, right? So these n minus 1 edges are incident to n minus 2 vertices. Then by pigeonhole principle, what happens? There is one vertex, at least one vertex has two fellows are incident, two edges are incident, right? I mean, there must be a set such that two fellows are incident. So from where they are incident? So these n minus 1 edges are coming from x and y. So it should be coming from x and y. It cannot be coming from x only because we are avoiding the situation of multi edges, right? It cannot be come from x only, it cannot be come from y only. So it should, two fellows has to come from x and y, right? So what is the contrast? So we have this thing is not possible, right? Set cannot be connected to x twice. So only possible thing is you have a x and one fellow, at least you are telling at least two edges incident to z. So this is one from here is a must, right? That's the idea. Okay, so this is the exact case also, right? You can't make many edges connecting from y to z because there is no multi edges. So then by pigeonhole principle, what happened is we got a fellow exactly in between x and y. So there is a connection. There is a path. X, Z, Y. There is a path, right? Yeah. So that means we took a x and y are arbitrarily and we got a path. That's they are connected. So the converse of this theorem or contrapositive of the theorem is very beautiful. If G is not connected, then there exists a vertex V such that the degree is at most n minus 1 by 2, strictly less than n minus 1 by 2. If G is not connected, there will be such a vertex available. So it's a negation implies right. So that's the idea. Okay. So these are two. There are many ways you can use PHP in many propositions. Even very beautiful, very strongest results are proved using PHP. For example, I can just give you an idea about Erdos-Sekres theorem. I will be doing this shortly after this clips. Erdos-Sekres, I don't know the spelling is Sekres theorem about sequences, and it's a very beautiful theorem. So that actually uses, there is a proof, the original proofs are I think not using this, but somebody gave a proof using pigeonhole principle. That's very beautiful. And that, so this is not a, even though it's a very common, I told you this principle is coming from very common sense, but the applications are groundbreaking, right? Yeah. Okay, so next we will see the further step in Schur's theorem. Okay, thank you.